Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
Welcome to the Deep Dive. Today we're exploring the answer to Quizzypedia Season 207, Question 3.
The category is physics.
The question is, what is the name of the hypothetical structure in spacetime that could connect two distant points in the universe, allowing for faster-than-light travel or shortcuts across vast distances? Often used in science fiction, this concept arises from Einstein's theory of general relativity and is also referred to as an Einstein-Rosen bridge.
The answer: a wormhole.
So let's dive into this concept of wormholes, examining the science behind them, their portrayal in science fiction, and whether they could actually exist.
To start, let's define what a wormhole is. Imagine a tunnel through space-time that connects two distant points in the universe. That's essentially what a wormhole is theorized to be. It's like a cosmic shortcut that could potentially allow us to travel vast distances faster than light.
Faster than light. That's pretty mind-blowing.
It is. And this idea goes beyond classical physics, offering a glimpse into a universe with some pretty extraordinary travel possibilities. You'll also hear wormholes referred to as Einstein-Rosen bridges.
Okay, so it sounds like something straight out of science fiction. But is there any real science behind this idea?
Yes, there is. The concept of wormholes emerges from Einstein's general theory of relativity.
So to understand wormholes, we need to understand general relativity first.
Exactly. In essence, general relativity explains that gravity is not a force in the classical sense, but rather a curvature of space-time caused by mass and energy.
Okay, I think I remember that from physics class. So how do wormholes fit into this curved space-time picture?
Picture space-time as a fabric that can be bent and warped. A wormhole is essentially a bridge or tunnel connecting two separate points in this curved fabric.
So instead of traveling the long way around the curve of space-time, a wormhole could provide a shortcut straight through.
Precisely. And what's fascinating is that wormholes aren't just a product of imagination, they are actual solutions to Einstein's field equations.
So the math of general relativity actually predicts these things could exist.
It does, but there's a catch. There are different types of wormholes. The simplest type, called Schwarzschild wormholes, are associated with black holes. However, these are non-traversable and unstable. They would collapse too quickly for anything to pass through.
So no cosmic shortcuts through those then.
Unfortunately not. For a wormhole to be traversable, meaning something could actually travel through it, we would need something called exotic matter. This exotic matter would have what's called negative energy density, which would be needed to stabilize the wormhole and keep the tunnel open.
Negative energy density. Can you explain what that means?
It's a bit complex, but essentially it means this exotic matter would have properties opposite to normal matter. Instead of having positive mass and energy that causes space-time to curve inward, it would have negative mass and energy that would cause space-time to curve outward, counteracting the inward pull of gravity and keeping the wormhole open.
Okay, I think I get it. It's kind of like blowing air into a balloon to keep it inflated. But this exotic matter, does it even exist? Has we ever observed it?
That's one of the biggest hurdles in the concept of wormholes. Exotic matter with negative energy density has never been directly observed in nature, so its existence remains purely hypothetical.
So where did the idea of wormholes even come from if we've never observed the stuff needed to make them work?
It all started back in 1935 with two brilliant physicists, Albert Einstein, whom we've already mentioned, and Nathan Rosen. They were working on solutions to Einstein's field equations of general relativity.
Ah, so this is where the name Einstein-Rosen bridge comes from.
Exactly. They were trying to find a way to eliminate singularities in black holes, those points where the laws of physics as we know them break down. They proposed the idea of a bridge connecting different regions of space-time, essentially creating a tunnel that bypasses the singularity.
Interesting. So their aim was to solve problems within black holes.
Yes, and they were also hoping to unify quantum mechanics and general relativity, the two pillars of modern physics. They envisioned these bridges as tunnels connecting different parts of the universe.
So even Einstein and Rosen, the fathers of this concept, hit a roadblock.
They did. Their calculations showed that these theoretical bridges would likely collapse too quickly for anything to pass through, making them more of a mathematical curiosity than a practical means of travel.
I guess that makes sense. But their work really sparked the imagination, especially in science fiction.
It certainly did. In science fiction, wormholes are often used for faster-than-light travel, allowing characters to traverse vast distances across the universe in an instant.
Think Interstellar, for example, with that giant spherical wormhole enabling travel to distant galaxies. And Contact uses a wormhole for interstellar communication. And then there's Stargate, where wormholes are gateways to other worlds.
Science fiction writers love wormholes because they offer a way, although currently unproven, to bypass the limitations of physics. It opens up all sorts of possibilities for telling exciting stories of interstellar exploration and encounters with alien civilizations.
And these stories make complex scientific ideas about wormholes more accessible and visually engaging for a wider audience.
Absolutely. Take Interstellar, for example. While it takes some creative liberties for storytelling purposes, the film portrays the science behind wormholes with a surprising degree of accuracy.
It really gets you thinking about the warping of space-time and the immense gravitational forces involved.
Yes, and by presenting these complex concepts in a visually stunning and narratively compelling way, science fiction has helped popularize the idea of wormholes and sparked curiosity about their potential reality.
Okay, but let's bring the discussion back to reality.
Ah.
Could wormholes really exist? We've talked about the theoretical framework, but is there any actual evidence for them?
That's the big question, isn't it? While wormholes are mathematically possible within the framework of general relativity, there's currently no observational evidence to confirm their existence.
So they remain a fascinating theoretical possibility, but a mystery nonetheless.
Exactly. And one of the biggest challenges to their existence is this idea of exotic matter with negative energy density that we talked about earlier.
Right, the stuff needed to stabilize a wormhole and keep it from collapsing. But you said we've never actually observed it.
That's right. However, there are some glimmers of hope. In quantum physics, something called the Casimir effect demonstrates that negative energy densities can actually occur.
Wait, so you're saying there's a real phenomenon in quantum physics that shows negative energy is possible? Could that be a clue that exotic matter might exist?
It's certainly possible. The Casimir effect shows us that negative energy densities are not completely out of the question. And some theories in quantum gravity and string theory suggest potential mechanisms by which wormholes could exist.
So even though we haven't directly observed exotic matter, there's a possibility it could exist.
Exactly. And one intriguing concept that comes out of those theories is the idea of quantum foam. This theory proposes that at extremely small scales, space-time itself is not smooth, but rather a turbulent sea of fluctuations.
So like a constantly bubbling and shifting fabric of space-time.
Yes, and within this quantum foam, tiny wormholes might constantly be popping in and out of existence.
Wow, that's pretty mind-blowing.
Mm.
Could these tiny fleeting wormholes ever be scaled up to a size we could actually travel through?
That's highly speculative. Making such wormholes large and stable enough for travel would be an enormous challenge requiring a level of control over space-time and energy that is far beyond our current understanding and capabilities. So even if these microscopic wormholes exist in the quantum foam, scaling them up for interstellar travel would be a whole other story. We're talking about manipulating the fabric of space-time on a massive scale, and that requires unimaginable amounts of energy.
It sounds like even if wormholes exist, using them for travel would present a whole new set of hurdles.
Absolutely. Even if we could somehow find or create a stable wormhole, the act of traveling through it would be fraught with challenges.
Like what? What kind of challenges are we talking about?
Well, the first challenge is stability. We've talked about how wormholes are theoretically very unstable and prone to collapse. Imagine stepping into a wormhole only to have it collapse around you instantly due to the slightest fluctuations in space-time.
Not a very appealing prospect. It sounds incredibly dangerous.
It would be. To prevent such a collapse, we'd need that exotic matter with its negative energy density to exert outward pressure and keep the wormhole open.
But we've already discussed how exotic matter is still hypothetical. And even if we could find it, how could we possibly harness enough of it to stabilize a wormhole large enough for a spacecraft, let alone a human?
That's the next major challenge. The sheer amount of energy required, estimates suggest it could be comparable to the energy output of an entire star, perhaps even a galaxy, depending on the size of the wormhole.
That's mind-boggling. Our current energy production capabilities are nowhere near that level. We can barely power our cities, let alone manipulate the fabric of space-time.
It would require a complete paradigm shift in our understanding of energy and how to harness it.
Yeah.
And even if we could somehow solve the energy problem, there's yet another danger to consider something called spaghettification.
Catification. That sounds unpleasant. What exactly did that involve?
It refers to the intense gravitational forces that would likely exist near the mouth of a wormhole. These forces could stretch and distort anything entering the wormhole. Picture a piece of dough being stretched and thinned into a long strand of spaghetti.
So even if we had a stable wormhole and enough energy to keep it open, we could still end up as cosmic noodles.
It's a real possibility. The tidal forces near a wormhole could be so intense that they would rip apart anything that entered, including spacecraft and humans.
It seems like every time we think about how to overcome one obstacle, another one pops up.
Mm-hmm.
So to summarize, we need exotic matter, which we haven't found to stabilize an incredibly energy-hungry wormhole. And even if we manage all that, we risk being turned into spaghetti.
You've got it. Interstellar wormhole travel, at least for now, remains firmly in the realm of science fiction. We simply don't have the scientific understanding or the technological capabilities to overcome these immense challenges.
That's disappointing, but also understandable, given how mind-bending this whole concept is. It's clear that there are still many mysteries surrounding wormholes. But are there any areas of research that offer some hope, or at least shed more light on these cosmic enigmas?
There are, and even though the practical applications of wormholes for travel may be a distant dream, their theoretical implications continue to fascinate physicists. They serve as tools to explore the relationship between gravity and quantum mechanics, particularly in the context of black holes and the information paradox.
Can you explain the information paradox for those of us who aren't theoretical physicists?
It essentially boils down to a conflict between two fundamental theories. Quantum mechanics says that information cannot be destroyed. However, general relativity implies that information that falls into a black hole vanishes into the singularity at its center.
So one theory says information is preserved, the other says it's destroyed. That's a pretty big conflict.
Yeah.
Do wormholes offer any way to resolve this paradox?
They might. Wormholes could provide a pathway for information to escape from a black hole, potentially preserving the principles of quantum mechanics. Some physicists theorize that information doesn't disappear into the singularity, but rather travels through a wormhole to emerge somewhere else in the universe, perhaps even in another universe altogether.
So instead of being destroyed, the information takes a detour through a wormhole. It sounds like something out of a science fiction novel, but incredibly intriguing nonetheless. I imagine wormholes also make physicists ponder the possibilities of time travel.
They do. The theoretical existence of wormholes, particularly those that could potentially connect different points in time, has fueled speculation about time travel for decades.
I remember learning about the concept of closed time-like curves in physics class. It's the idea that a path through space-time could loop back on itself, theoretically allowing travel to the past.
Exactly. And some physicists believe that wormholes could, in theory, create such closed time-like curves. However, this raises a whole host of paradoxes and challenges our understanding of cause and effect.
It's like the classic grandfather paradox. What if you go back in time and accidentally prevent your grandparents from meeting? Would you cease to exist? These are questions that have fascinated philosophers and scientists for centuries.
They have. And while the possibility of time travel through wormholes is highly speculative, it's a testament to the power of theoretical physics to push the boundaries of our imagination and make us question the very nature of time itself.
It's a bit overwhelming to think about all the potential implications. But even if wormholes never lead to time travel, they certainly spark some fascinating discussions about the nature of time and causality. Are there any recent advances in theoretical physics that have shed new light on the mystery of wormholes?
There are some intriguing developments. One that has garnered a lot of attention is the ER-EPR conjecture proposed by physicists Leonard Susskind and Juan Maldacena.
ER-EPR. That sounds like a secret code. Can you break it down for us?
It stands for Einstein-Rosen equals Einstein-Podolsky-Rosen. It proposes a deep connection between wormholes, or Einstein-Rosen bridges, and quantum entanglement, which is described by the Einstein-Podolsky-Rosen paradox.
So it's linking wormholes to quantum entanglement. That seems like a pretty radical idea. Remind us what quantum entanglement is again.
Imagine two particles that are linked in a way that defies our classical understanding of physics. No matter how far apart they are measuring, the state of one particle instantly determines the state of the other. This spooky action at a distance, as Einstein called it, is what lies at the heart of entanglement.
So even if these particles are light years apart, they act as if they are connected by an invisible thread.
Exactly. And this interconnectedness has been experimentally verified many times. It's a fundamental aspect of quantum mechanics.
Okay, so we have these two seemingly separate concepts. Wormholes described by general relativity and entanglement described by quantum mechanics. How does the ER-EPR conjecture connect them?
It proposes that these entangled particles might actually be linked by microscopic wormholes.
So instead of some mysterious instantaneous action at a distance, the entanglement could be explained by a physical connection through these tiny wormholes. That's pretty mind-blowing.
It is. It suggests that entanglement is literally weaving the fabric of space-time itself, creating these minuscule wormhole connections between particles.
That's a radical shift in how we think about both entanglement and space-time. It's like saying that the universe is fundamentally interconnected at a level we never imagined.
Exactly, and it challenges the long-held view that quantum mechanics and general relativity are separate, incompatible theories. The ER-EPR conjecture suggests they could be intertwined at a fundamental level.
So gravity, which shapes the large-scale structure of the universe, might emerge from entanglement, this quantum phenomenon that connects particles in a seemingly non-local way. That's a pretty profound idea.
It is. It suggests that the very fabric of space-time might be woven from the threads of quantum entanglement.
But is there any evidence to support this conjecture?
It's still a very speculative idea, and experimental verification is extremely challenging. But there are theoretical arguments and mathematical models that suggest it's a plausible possibility.
What kind of arguments? What does the math tell us?
One compelling piece of evidence comes from the geometry of space-time. The mathematical equations describing wormholes and the equations describing entanglement show remarkable similarities. This hints at a deeper connection between these two seemingly disparate concepts.
So the math seems to be pointing towards a link between wormholes and entanglement.
It is. There are also thought experiments and theoretical models that explore how entanglement could give rise to wormhole-like structures in space-time.
Can you give us an example of one of these thought experiments?
One famous thought experiment involves creating a pair of entangled black holes. As these black holes become increasingly entangled, the geometry of space-time warps in a way that resembles the formation of a wormhole connecting them.
So the entanglement of these massive objects could actually bend space-time to create a bridge between them. That's incredible.
It is. It's a highly theoretical scenario, but it illustrates the potential for entanglement to have a profound impact on the structure of space-time.
This ER-EPR conjecture is definitely pushing the boundaries of our understanding of the universe. It's both fascinating and incredibly challenging to wrap our heads around.
It is. But that's what makes it so exciting. It's
Yeah.
pushing us to reevaluate our fundamental assumptions about the nature of reality and the relationship between space-time gravity and the quantum world.
Even if it turns out that this conjecture isn't entirely correct, it's clear that it's sparking a lot of new research and pushing the boundaries of theoretical physics.
It is. And it's a reminder that we still have much to learn about the universe and the laws that govern it. Wormholes, once considered a purely speculative idea, have become a catalyst for exploring some of the deepest mysteries of physics.
Speaking of mysteries, what about those potential applications of wormholes we discussed earlier? Instantaneous communication, understanding consciousness, even the potential for time travel. While they seem like science fiction, are they based on any real theoretical possibilities? They do sound like science fiction, but then again, so do a lot of things we now take for granted.
Yeah.
So is there any chance that any of those applications could become reality?
Well, let's just say the technological hurdles to realizing any of those applications are immense. We would need to find or create stable wormholes, somehow overcome the energy barriers we talked about, and figure out how to address those safety concerns like spaghettification.
It definitely doesn't sound like we'll be stepping through a wormhole to visit another galaxy anytime soon.
Probably not.
Yeah.
But it's still fascinating to consider the possibilities. Imagine a future where we could communicate across vast distances instantly. Instead of relying on signals that travel at the speed of light, we could transmit information through a wormhole and it would arrive at its destination instantaneously.
It would completely revolutionize communication, especially for space exploration. We could communicate with probes and spacecraft in distant parts of the solar system, or even beyond in real time.
Exactly. No more waiting years for signals to travel back and forth. It would open up a whole new era of space exploration.
And you mentioned the possibility of wormholes playing a role in understanding consciousness. That's a pretty wild idea.
It is. But if information can be transmitted through wormholes, some physicists speculate that our consciousness, our thoughts and experiences, could also be somehow connected through these tunnels in space-time.
So instead of our consciousness being confined to our brains, it could be non-local, spread out across the universe, connected by these quantum wormholes. That's a pretty radical concept.
It is. It ventures into some pretty profound and philosophical territory, but it highlights just how much we still don't understand about consciousness and the nature of reality itself.
It seems like every time we talk about wormholes, we end up with more questions than answers. But it's clear that the concept has sparked a lot of imaginative thinking and inspired countless scientific inquiries. Even if wormholes never become a practical reality, they've enriched our understanding of the universe.
Absolutely. Wormholes force us to rethink our assumptions about space and time, and they highlight the deep connections between gravity and the quantum world. They remind us that the universe is far stranger and more wondrous than we can possibly imagine.
Well, I think we've covered a lot of ground today. We've gone from the basics of general relativity to mind-bending concepts like exotic matter, quantum foam, and the ER-EPR conjecture. It's been a pretty intense deep dive. What are some key takeaways you hope our listeners will remember?
First, I hope they appreciate the elegance and power of Einstein's general theory of relativity. Wormholes, as bizarre as they sound, emerged naturally from the mathematics of this theory. Second, I think it's important to understand that even though wormholes are theoretically possible, the challenges of actually using them for travel or communication are immense. We're talking about manipulating the fabric of space-time on a scale that's beyond our current comprehension.
And lastly, I think the most important takeaway is that the universe is full of mysteries. Wormholes represent just one of many enigmas that continue to challenge our understanding of physics and inspire us to keep exploring the unknown.
Exactly. And as we delve deeper into these mysteries, we're bound to encounter even more astonishing concepts and ideas that will stretch our imaginations and push the boundaries of human knowledge. The journey of scientific discovery is never ending.
Thank you for joining us on this deep dive into the fascinating world of wormholes. We hope you've enjoyed exploring this mind-bending concept and that you'll continue to join us as we delve into other mysteries of the cosmos.
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.